this episode, we are looking at a part of artificial intelligence, AI, testing that often determines whether a system feels trustworthy or merely impressive for a short time. A model can produce strong-looking outputs, pass broad performance checks, and still carry serious risk if no one understands why it behaves the way it does, what patterns it relies on, or where its confidence becomes misleading. That is why interpretability matters so much during testing. It helps the organization move beyond the surface question of whether the output looked acceptable and into the deeper question of whether the system is behaving in a way people can understand, supervise, and correct before real users depend on it. When interpretability is weak, model risk tends to hide behind polished language, average scores, and apparent efficiency. When interpretability improves, testers can see more clearly where the model is sensible, where it is brittle, where it may be overreaching, and where the design should be narrowed or strengthened before deployment. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Interpretability is best understood as the ability to make sense of how a model is behaving well enough to support human judgment. It does not require that every person can inspect every internal mathematical detail, and it does not mean the system becomes perfectly transparent in a literal sense. Instead, it means the organization can understand the model's behavior at a useful level. People testing the system should be able to see what kinds of inputs lead to certain outputs, what signals seem to influence the result, what conditions make the model less reliable, and whether the reasoning pattern matches the intended use case. For beginners, this is a very practical idea. If the system gives a recommendation, ranking, classification, or draft, the team should be able to ask why that happened and get an answer that is meaningful enough to support review. If the team cannot do that, then the system becomes much harder to govern because it is asking people to trust something they cannot properly examine. Model risk is the broader problem that interpretability helps reduce. Model risk means the possibility that the system will produce harmful, misleading, unstable, unfair, or poorly governed outcomes because of weaknesses in the model, the data, the design, or the way people use the output. Sometimes the risk comes from technical error. Sometimes it comes from hidden assumptions in the data. Sometimes it appears because the model is used for a purpose that stretches beyond what it was tested to support. Another common source of risk is over-reliance, where people trust the system too quickly because it sounds confident or looks efficient. That is why model risk is not just about whether the algorithm is wrong in a narrow technical sense. It is about whether the full system, including the people around it, can produce outcomes the organization cannot explain or defend. During testing, interpretability becomes one of the clearest ways to expose that risk before it shows up in real decisions, real workflows, or real harm. One reason interpretability belongs inside testing rather than after testing is that broad performance scores can hide dangerous behavior. A model may look strong on average while failing for the wrong reasons on specific kinds of cases. It may succeed because the test set contains clues that are easier than real-world conditions. It may appear accurate because it learned shortcuts that happen to line up with the test data but do not reflect the true task. Without interpretability, the team may see a good score and assume the system is ready. With interpretability, the team can ask whether the model is actually paying attention to the right kinds of information or merely getting acceptable results through patterns that are fragile, accidental, or inappropriate. This is one of the most important shifts in mature testing. The organization stops treating performance as the only question and starts asking whether the path to that performance is stable enough, fair enough, and understandable enough to support deployment. A useful way to improve interpretability during testing is to examine the model at two levels at once. The first level is overall behavior across many cases. This helps the team understand whether the system generally performs in ways that match the approved purpose, whether certain case types cause repeated trouble, and whether the model is leaning on patterns that seem too shallow or too narrow. The second level is case-specific behavior. This helps the team understand why the model produced a particular result for an individual example and whether that result makes sense given the input and the surrounding context. Both levels matter. If testers focus only on overall behavior, they may miss the fact that certain individual cases reveal serious weaknesses. If they focus only on single examples, they may miss broader trends that point to a deeper design problem. Strong interpretability work combines both views so the organization can understand the model as a pattern-making system and also as a tool producing specific outputs that people may rely on in specific situations. This becomes much easier when the testing plan includes a thoughtful mix of cases rather than only routine examples. To improve interpretability, the team should look at ordinary cases, difficult cases, edge cases, contradictory cases, messy cases, and out-of-scope cases. Routine examples show whether the system behaves sensibly in normal use. Difficult and edge cases show where the model becomes uncertain, inconsistent, or overly confident. Contradictory and messy cases help reveal whether the model can separate strong signals from distracting noise. Out-of-scope cases are especially important because they show whether the system knows when it is outside its lane or whether it keeps producing confident-looking outputs even when it should slow down or defer. This type of testing improves interpretability because it exposes the patterns behind model behavior. The team begins to see not just when the model fails, but what kinds of conditions make failure more likely and whether those conditions are common enough to require design changes, stronger controls, or narrower use. Another helpful practice is to inspect the relationship between the input, the output, and the supporting evidence the system appears to rely on. When testers review a case, they should ask whether the output is anchored in information that is actually relevant to the task or whether it seems driven by superficial clues. A system may produce a very polished answer while leaning too heavily on one phrase, one formatting signal, or one historical pattern that should not carry so much weight. In some designs, the team may review feature influence, supporting retrieved context, ranking signals, or natural language rationales the system provides about its own output. That last category can be useful, but it should be treated carefully. A plausible explanation is not always a truthful one, and a model may produce a smooth rationale that sounds coherent without accurately reflecting what drove the output. This is why interpretability during testing is not about accepting every explanation the model offers. It is about checking whether the apparent basis for the result aligns with the real task, the real evidence, and the team's own domain judgment. Human review sessions are another powerful way to improve interpretability and reduce model risk during testing. These sessions work best when the people involved understand the use case well enough to recognize when a model is missing context, overreacting to weak signals, or sounding more certain than the case deserves. A reviewer does not need to know the deepest mathematical details of the model to contribute value. What matters is that the reviewer can compare the output against the input, the workflow, and the purpose of the system. When several reviewers examine the same kinds of cases, patterns start to emerge. They may notice that the model is strong on straightforward examples, but weak when language is indirect, when evidence is mixed, or when the task requires more caution than the model naturally shows. These sessions also help identify over-reliance risk. If human reviewers begin accepting outputs too quickly during testing, that is already a warning sign that the system may be shaping judgment more strongly than intended and may need interface or workflow changes before it reaches live use. Interpretability is especially valuable for finding shortcut learning, which happens when a model learns a pattern that helps on the training or test data, but does not reflect the real thing the organization wants the system to understand. A model might learn to associate urgency with certain words while ignoring the broader context. It might treat length, grammar style, or formatting as stronger indicators than they deserve. It might latch on to clues that correlate with the answer in one environment, but would fail badly when the context changes. These shortcuts can remain hidden if the team only tracks whether the final answer looked right. Interpretability helps bring them into view because testers begin asking what the model is really responding to. Once those weak patterns are visible, the organization has more options. It can revise the data, adjust the scope, redesign the workflow, create stronger review requirements, or change how the system is allowed to present uncertainty. That is how interpretability reduces model risk. It helps the team detect fragile success before fragile success becomes a business habit. Uncertainty is another major area where interpretability and model risk meet. A system becomes much safer when testers can tell not only what output it gives, but how stable that output is across harder conditions and how much caution the design should attach to it. During testing, the team should examine when the model becomes hesitant, when small input changes produce large output shifts, and when the system keeps sounding confident despite weak evidence. These patterns matter because an uninterpretable model may encourage people to treat every output as equally trustworthy. A more interpretable testing process helps reveal where the model should be allowed to act more directly and where it should defer to human review, additional evidence, or a narrower workflow. This is why thresholds, escalation rules, and abstention behavior belong closely beside interpretability. The organization needs to know not only how to understand the model when it speaks, but also when the model should be designed to say less, act less, or step back from the decision altogether. Comparing model versions is another powerful testing practice because interpretability is not only about one model in isolation. It is also about whether changes make the system clearer, safer, or harder to govern. A new model version may improve speed or general performance while becoming less stable on edge cases. A data update may improve one group of examples while weakening another. A threshold change may reduce false alarms, but also hide cases that deserve attention. Without interpretability, these trade-offs are easy to miss because the team may focus only on the most visible headline metric. With interpretability, the team can compare not just outputs, but behavior patterns. It can ask whether the new version relies on stronger evidence, shows better restraint, handles ambiguity more honestly, or introduces new kinds of confusing behavior. This is one reason documentation matters so much in testing. The organization needs a record of what was changed, what interpretability findings emerged, and why a version was approved despite any remaining limitations. Interpretability also strengthens fairness and security testing because both areas depend on understanding how the model reaches its results. If a system performs worse for certain groups or contexts, the team needs more than a performance gap. It needs to understand what patterns may be creating that gap. Are some language styles being misread? Are certain inputs consistently missing context the model depends on? Is the system overvaluing proxies that align unevenly with different populations? Security questions work the same way. If a model becomes easier to manipulate under certain phrasing, formatting tricks, or misleading context, interpretability helps reveal what the system is responding to and why the attack works. That makes mitigation much more effective. Instead of only knowing that a weakness exists, the organization begins to see how that weakness is expressed in model behavior. This allows more precise changes to data handling, prompt structure, review rules, and scope limits, all of which help reduce model risk before deployment grows broader and more costly to correct. A mature testing program also recognizes that interpretability does not have to mean total simplicity. Some models will remain complex, and some behaviors will never become perfectly transparent in a complete, human-readable way. The goal is not to force every system into a false sense of total openness. The goal is to achieve enough understanding to support trustworthy decisions about approval, oversight, limits, and risk treatment. That means the organization should ask a practical question. Do we understand this model's behavior well enough to know where it works, where it weakens, how it fails, what evidence it seems to rely on, and what controls are needed around it? If the answer is no, then the model risk is usually higher than leaders want to admit. In some cases, the right response is to improve interpretability through better testing and better review. In other cases, the right response is to narrow the use case, add stronger human control, or choose a simpler approach that the organization can govern more confidently. By the end of this topic, the most important lesson should be clear. Interpretability improves AI testing because it helps the organization look past smooth outputs and ask whether the model is behaving in ways people can understand, challenge, and supervise. That matters because model risk often hides inside systems that seem strong until someone examines the reasoning pattern, the shortcut, the uncertainty, or the uneven performance underneath the surface. During testing, better interpretability helps expose fragile success, overconfidence, spurious patterns, and hidden dependence on the wrong kinds of signals. It also supports stronger human review, better thresholds, safer escalation rules, and more honest version comparisons. The result is not perfect certainty, and it does not need to be. The result is a system that is easier to question and therefore easier to govern. That is the real goal of improving interpretability during testing. It gives the organization a better chance of catching model risk while change is still possible, instead of discovering that risk only after people have already begun to trust the system too much.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.